All right, now let's study the Hello World smart contract. Our first step into writing the step-by-step crowdfunding smart contract. Our goal is to write the Hello World contract, understand what the validator script is, define wallet actions, register the contract endpoints, and compile and simulate it. Let's see how that works out. So we go to the Plutus playground, and our first step is we need to delete everything that is there. To get started. Okay. So the first thing, as with any Haskell program, we will start with the proper import. So we will import these modules that are part of the Plutus language. And you can check what this import means in the reference material that is linked on this video. Okay, so first we have our imports. As you know, in Haskell there are multiple ways to import code from other modules. Here we use both qualified and unqualified imports, which is, qualified and unqualified. Then, when we use a qualified import, we can make sure that the expression with the same name in other modes will not clash. You can read more about the topic in the reference material on the links. Now, let's look at the validator script. The validator script contains the on-chain Plutus code, so that's what is gets stored in the smart contract, to be evaluated distributedly by the slot leader of the network. It's a lambda expression that takes three values. The redeemer script, that is the expression provided by someone attempting to redeem the contract funds. The data script, with the expression associated to each UTXO currently assigned to the contract. The pending transaction provides the current block state that could be used to determine if the transaction is valid or not. Here, the current slot height. And is written in template Haskell to allow on-chain code to be written in the same file with the off-chain code. And technically, it is a type validator script. So in our case, let's go to write our validator script. Let's do something like this. We are going to do my validator script, that is subtype validator script, and the code would be, my validator script that comes from the validator script, and then we use this lambda expression to say what it means. Not like this. Okay, now we have it. Something that, there you go. Until it looks nicer. Okay, nice format. All right, now, the on-chain code is defined between the operator bracket pipe delimiters. This means that the on-chain code for this validator script is actually this expression right here, this lambda expression. This lambda expression has three arguments. The data script data, here we give it of type unit. Later we will change this. Then we have the redeemer script data, this one here, that is going to be provided by the user attempting to redeem the data from the contract, and the pending transaction data, this one right here. In our case, we don't care in this contract about the value. So that's why we use the underscore there. And for the time being, our whole land expression is of type unit, because currently we don't really care what is going to be executed on chain. So since we are returning the unit value, no real validation is being performed. Now, look at how we use the compile script function of the ledger module. This is a Plutus function that directly takes our on-chain expression and its result is spliced in our Haskell code. That's what this operator does. That's what the $$ operator does. It transforms our Plutus expressions and turns them into Haskell code. This expression is what is taken to construct the validator script we need. So that's the validator script. Now we are going to register smart contract endpoints. So let's first. Now that we have defined our validator script, we should define a wallet action in our contract. Wallet actions are Haskell expressions with the type monad wallet type to a monad unit. That is, expressions evaluated in a monad wallet context. Expression with this type serve as contract endpoints. Users' wallet can interact with our smart contract through these functions. For example, let's add a wallet action that just logs hello world to the console logs. So here we have the function hello action, that is, the context monad wallet, and then we use the wallet log message hello world. We use the log message functions from the wallet module and give it the message we want to log out, hello world. In order to be able to interact with the wallet actions from the playground, we need to register it as a contract endpoint. This is done using the mk function at the end of the file, like this. You see? Here we have the hello action register. Note that the mk function takes a list of actions to register the map. For the time being, we just have one action, but we still need to specify as a list. Okay, so now that our contract is running, we can compile it. If we go to the simulation pane, here we can see wallet 1, and here is the hello action, the one that we defined and it's available to use. So we will use a hello action. Then we're going to wait 10 slots, and we're going to let wallet 2 perform also a hello action. If we evaluate this code, the simulation, well, first of all, the fee and the balances all remain the same as when they got created. The important thing for us is here in the logs. Observe how wallet 1 says hello world, and then wallet 2 also says hello world after waiting 10 slots. And this is the compilation of the smart contract. So, just to reiterate, our basic smart contract will require a validator script, which is the on-chain code we are going to use, actions of the type monad wallet, And then we need to register those actions as entry points for the smart contract using the MK function. Alright, so congratulations, this is our first smart contract in Plutus. Although, doesn't do a lot. We are going to keep increasing this code in following examples.